Welcome. My name is Esther Robles. I'm from Rediris, the National Research and Education Network in Spain. So welcome to this session where we will see some different developments for planning, managing, and accessing the capacity as a resource, as a network resource. Our first speaking is Laia Ferraro. She comes from Barcelona, from the I2CAT Foundation, where she is working as a researcher network. So, Laia?
Este cable no sirve para nada, ¿verdad? Esto de aquí, ¿qué? Esto de aquí no sirve para nada, ¿verdad?
No, yo creo que no.
Hello? Okay. One, two. Is it okay? Okay. Well, my name is Laia Ferrao, and I'm going to present the paper called Advanced and Immediate Reservations of Virtualized Network Resources. This paper talks about two projects. The first one is called Chronos, and is a reservation system that allows users to perform advanced and immediate reservations of network resources. The second project is called Argia, and is a middleware that allows users to virtualize network resources. This is the index that I'm going to follow. In the first place, I'm going to make a little introduction. Then I'm going to go deep into Argia, Chronos, and then I'm going to explain what is HPDMNet, that is a real case where Argia and Chronos are applied. I'm going to present also the demonstration that took place in the SCO8 of the HPDMNet, and at last I'm going to present the conclusions and the future work. So let's start with the introduction. To make you understand why Argia has been developed, I'm going to tell you a little story. It's a fictitious example, not a real one. So imagine these three cities: Rome, New York City, and Barcelona. In these three cities, there is a company, and this company has one site in each city. The company wants to buy a physical network in order to transfer data between the sites. And as this data is very sensitive and very important for the company, it is needed an infrastructure for the company only. But in these cities, there is also the universities. And for example, these universities are working in a very important international project, and they have to transfer a lot of data. So they also want a physical network for their own. But there is a very big problem: the actual economical crisis. They don't have enough money to support this very big cost. They can't buy a physical network. The University of New York City is very worried because it's very interested in taking part in this project. So the University of Barcelona suggests to share the resources. But the company doesn't rely on this fact because the data that they have to share is very sensitive. And also, the company doesn't want that the universities collapse the network with all the data that they are going to transfer. But Barcelona has an idea. He has heard about a software called Argia that allows to share the same substrate and use this substrate as if the universities and the company belong the network. So finally, all of them decide to share the same physical network in order to save money. So this is the physical network that they have bought. And now they are going to use Argia to divide this network into virtual networks. The first step is to virtualize the switches. And for example, these 4 optical switches have been virtualized in 2. The next step would be to create the links for the network of the company. For example, these ones. And finally, the links for the universities. And this would be the final network. So we have 2 virtual networks working on the same physical substrate, and they are sharing a physical network, but they are independently. So we have the middleware Argia that allows users to treat network resources as software objects and can provision and reconfigure connections within a single domain or across multiple independently managed domains. The second project that I mentioned, Chronos, is a reservation system that allows users to perform advanced and immediate reservations of the network resources virtualized by Argia, and it is not necessary to know the inner topology of the network. And the real case where Kronos and Arja are applied, the HPDM net, is a network research initiative that is developing a service used for applications that require to transfer a lot of data. So now I'm going to explain better what is Arja. First, I have to talk about infrastructure as a service. Infrastructure as a service is renting hardware using software services. And in this way, the user owns and controls the infrastructure if he was the owner during the period of time that he has rented these services. The AAS framework is a set of resources, libraries, and tools that enable developers to quickly create new infrastructure as a service solutions based on the framework programming model. So Arja is the infrastructure as a service framework-based system that allows to create infrastructure as a service solutions, but for optical networks. Sorry. Arja is the evolution of the software called UCLP version 2. UCLP version 2 was just a prototype, but now Arja is evolving to a commercial version. There are three types of users in Arja. The first ones are the infrastructure provider, which are the ones that own the physical network, the infrastructures, and give permissions to other users in order to use these infrastructures. That this would be the virtual network operator, which uses these resources given by the infrastructure provider and create a virtual network that will be used by the end user. The main goal of RJSO is to enable infrastructure providers to partition the physical network or the infrastructure, and in this way give the control to third parties during a certain period of time. And these third parties can, for example, use the partitioned infrastructure in-house, or can also deploy some intelligent software like Kronos to provide services for their end user, or also can partition the infrastructure in order to rent it to other users. So now I'm going to explain how Kronos works. Kronos, as I told before, is a reservation system that allows users to create reservations in advance or immediately. And it is not necessary to know the inner topology because Kronos handles routing. So the users just have to select the endpoints to connect. It can be point to point or point to multipoint. Also have to select the start and end times and the bandwidth needed. And the Kronos systems will find the best path using the Dijkstra algorithm and will reserve the resources if they are available at the requested time. There are two possible users in Kronos. The first one would be a human person like us. We can use Kronos through the web client, or a Grudelmer, like for example, the Harmony project that currently is using Kronos to create reservations. How Kronos interact with Arja? As you can see in this image, the end users can contact Kronos by the web client if the user is a human user, or by the web service if it's a grid middleware. And Kronos calls Arja when the connections have to be activated or deactivated. Now I'm going to explain the real case where the Arja and Kronos systems are used. The high-performance digital media network. Well, a group of centers that are the members of the HPDM net has formed this cooperative partnership that address key challenges and the opportunities related to using dynamically provisioned light paths for high-performance digital media. The HPDM net initiative is designing a glyph service that will be used for applications that require a lot of bandwidth. The testbed of the HPDM net has multiple sites within the glyph infrastructure in North America and also in Europe, and the network is dynamically provisioned by Arja and Kronos. The demonstration that took place in the SCO8 of the HPDM net had one main goal, that was to create a level 1, level 2 network instantiation composed by resources from different physical networks. And reservations end-to-end were created between these different sites to stream video in high definition. These physical networks were from the Pacific Wave Gold, Starlight Gold, Canary, a testbed of Nortel networks at Ottawa, Netherlight, I2CAT, Sarah, and Yuva. Arja was used to create the network by means of virtualizing the resources, but only from the first 4, from Pacific Wave Gold, Starlight, Canary, and Nortel. And the other ones were added in the testbed manually because the switches that are in these domains are not yet supported by Arja, but in the future they will be also. And Kronos was used to create the reservations of the available resources. In the following slides, I'm going to show you how these resources are virtualized using Arja. In these ones, the first one, we can see the first step of the process. The infrastructure providers must create the physical network in each domain using the resource management center that is the user interface of the Arja. The second step is to virtualize the resources in each domain and export them to iCare, which there will be the virtual network operator of the HPDM net. And then the resources must be imported by this user, by the administrator at iCare. And finally, links were created between each domain. And at this point, we have the testbed of the HPDM net created, and users can create connections, reserve resources using the Kronos, or can also partition or burn resources using the RMC of Arja, etc. And all without having to contact the network administrators from each domain. And in this image, you can see the final image of the testbed. As I said before, these ones have been created using Arja, and the other one manually. How Kronos was used in the demonstration. Kronos was used to create some reservations from each domain to the venue that was located at Austin, Texas. And some reservations were created specifying a relative start time between them. For example, 5 minutes between one reservation and the other one. And to prove that the connections were created correctly, video streaming in high definition was used. In this image, you can see a screenshot of the web client Kronos. Here, you can see the list of the reservations that are created, and if you click on the service of the reservation, you can see information of the service, for example, the start and end times, the status, etc. And in this site are the different functionalities that the user can perform with the reservations. For example, the net can be reloaded to check if some change in the network has been done. The user can check if the reservation is available before creating it, also create a reservation, and delete reservations. For example, all, some, or one specific. In this screenshot, you can see the wizard to create a reservation. As you can see, the user have the possibility to create a prior reservation. This is because if the user is not sure that he wants to perform this reservation, he can create a prior reservation and then in the future make it permanent. The reservation can be fixed or malleable, can be also in advance, for example, tomorrow at 10 o'clock or now immediately, and also can indicate a relative start time. For example, start the connections after an hour of the reservation number 10, for example. And also select the start time, the end time, the end points, for example, point-to-point or point-to-multipoint. Here we have selected 3 destination endpoints, but it can be only one also. And just click on OK, and the reservation, if it's possible, will be performed. If it's not possible, a message indicating that in the requested time is not possible, but maybe an hour later it will be possible. And in this screenshot, you can see information about the available endpoints to create the reservations. If you click on an endpoint, you can see where it is placed and information, the IP, the name, etc. The conclusions of the paper, I can say that, well, I said already, but Arja allow multiple users to share the same substrate. And the users can create their own isolated network by means of virtualizing the network resources. Kronos using Kronos, the users can perform advanced and immediate reservations of the virtualized resources by Arja, and it is not necessary to know the inner topology. An advantage of Kronos is that the users can know in advance if the resources that they will need are available or not. And finally, the future work. At present, there is no commercial version of Arja, but we are working on it. Kronos will be able to perform reservations using Ether, that it will be the equivalent of Arja, but for Ethernet connections. And the HPDMnet testbed is being extended to Asia and in the future to other places. And that's all. Thank you for your attention.
Okay, you said that you can perform advanced reservation that could be fixed or malleable. Could you elaborate a bit more about this, please?
Well, we can go through that slide. Okay, a fixed reservation is, for example, I want to reserve resources from Barcelona to Paris on Monday, 6th of June, from 10 o'clock to 12. And this is fixed. I want to transfer data in these 2 hours. But malleable, the user can say, I want to transfer 3 gigas of data, for example, and I want that this data be transferred on Monday, but I don't mind the time. And the algorithm on Kronos, will find a gap to perform this connection, and it would be, for example, if the user says from 9 o'clock in the morning until 9 o'clock in the evening, and if at 9 o'clock is possible, the reservation will be performed at 9, no at 10 or at 11. Is clear what is malleable reservation? Or? Okay.
I would like to know if the system allows to mix the layer 2 technology. I mean, if it is possible to make reservations between the different domains and within each domain using, for example, SDH, Ethernet, to mix the technology.
Well, at the moment, it's only for optical networks because RGA is working only with optical networks. In the future, it could be.
Okay, thank you, Laia. Welcome. Our next speaker is Klaus Grobe. He is currently working at ADVA as a principal engineer in optical networking. Yes, your presentation should be there. Let me close this, and here. That one?
Yeah. Okay, thanks, Esther. Good afternoon, everybody. I will again talk about optical transport. ADVA is still a transport company. That didn't change since yesterday. Again, I will not talk about 100 gigabit Ethernet transport. I think I did that last year. I will focus on another area which is, I hope, interesting for this community. It's certainly a hot topic in telecommunications for more than one reason, and that is ultra broadband next generation access. And my co-author on this paper is Jörg-Peter Elbers. This is the outline. I will present a few slides on broadband access and one of the drivers behind certain solutions, which is energy efficiency. I will not talk about the content drivers and the application drivers. I think you know them better than me. Then there are a few slides on NRANs. One of the slides I showed yesterday already. Having, or whatever, broadband access, and then I will present from our viewpoint, the main contenders for broadband access transport. Okay, first section, broadband access and energy efficiency. I think this is the only long text slide I have. There are, in the NRAN context, there are, from our point of view, two different applications. It's either broadband, and that means maybe multiples of gig-E services, possibly 10 gigabit Ethernet services. Yes, I talked about InfiniBand yesterday, possibly that as well. In the future, 40 gig, whatever comes at hand. And then there may also be the case that you need ultra broadband connections, sort of access between two sites, which I talked about yesterday. Typically, these networks, the access networks, have hence to support every high bit rate services or protocols, Ethernet, whatever else. And they should provide dedicated bandwidth, possibly also secure bandwidth or services. So I don't think that a shared medium as we see it today in telco access would be a solution. I will touch upon that later. And then there is good reason to require some specifications like high access reach. And when we talk high reach in the access, that means 100 kilometers plus. We are not talking last mile. We are talking up to 100, 120, whatever kilometers. I will touch on the reasons for that one. As already mentioned, we need very high per client or per customer per site bandwidth, and hence, since we are logically in most cases talking point to multipoint, also of course very large accumulated bandwidth. And then yes, it has to be kept as simple as possible, as cheap as possible, as low in energy consumption as possible. And as I will show, an optimized access network, which needs to be an optical one, no alternative, can help eliminating active sites. Active sites means sites where active transport equipment is located, which makes things cheaper for obvious reasons. It can possibly eliminate or integrate into the, well, WDM transport an aggregation layer, if that is useful for your networks. And overall, and amongst others due to the high reach requirement, it can help consolidate the number of compute sites or active sites in general in a large network. And that is relevant for total energy consumption of the complete network, which I will show in a moment. Obviously, energy in networks is now becoming an issue. You all know the keyword green IT. Data centers and telco altogether are in the range of 10% of the worldwide electricity production. And estimations exist that say, should bandwidth requirement increase ever more, and we don't do anything about energy consumption, we may end up with something like 50% of energy production, electricity production. That is one driver. The second one is not only we are consuming more and more energy, unfortunately, energy is getting more and more expensive, and in particular in the last 4 years, we saw some 30% increase both in Europe and the US. So it's getting more expensive anyway. So there's good reasons to try to optimize the networks in terms of energy consumption. This diagram I took from Jerry Epps from Cisco, who found out where the energy is consumed, mainly if we consider large networks with data centers. And as you can see, the majority is consumed in the IP engines. So layer 3, next the majority is consumed for heat, ventilation, air conditioning. That is relevant. because every bit of energy consumed that we save here, we in addition also save there. But from what we really need for compute power, etc., the majority is needed in the layer 3. Second then is, where is it? Switch fabric, that is mainly layer 2, plus control plane if there is one. Well, I assume there is. And only some 7% are used for I/O, which means for WDM transport. In other words, wherever we can replace a higher layer functionality by a lower layer one, do so. And how can we do it? By consolidating sites into less sites with bigger machines, because that has been shown that the same compute power, the same layer 3, layer 2, whatever functionality, put into one bigger machine does consume less energy as the same accumulated compute power spread or dispersed geographically in more smaller machines. But should we go that way, consolidate into less sites with bigger, data centers, we obviously need long distance access, 100 plus kilometers. So that's the story. NRANs with broadband access. I showed that slide yesterday. I produced it specifically for this event. This is my view on a generic NRAN. So we have I must stay here. We have the backbone. This is where we will see in 2-3 years from now multiple 100 gigabit Ethernet transport with transponders consuming 500 watts as was pointed out yesterday. And then we have access in potentially large regions. So I'm now talking about these structures here. Logically point to multi-point, and I learned in a discussion today, this is really a relevant scenario because, for example, all these fibers may be leased or bought from a fiber provider, and that one may have only a single fiber pair between the backbone or the backbone sites and a logical fiber hub site here. And then there is fibers going out to various sites. So this can either be a large campus or really a region with, say, up to 100 kilometers. Typically, these structures are solved in telco access with a technology called PON, Passive Optical Networks. Passive refers to the fact that this site here can be a fully passive site. So no need for power supply, no need for heat, ventilation, air conditioning, no need for stuff, cheap, passive, highly reliable. Unfortunately, the standard telco PON system, there are some standards. I will not go into too much of detail here, but the standard PON systems in telecommunications are splitter-based. That means here is a power splitter, and they are using 2.5 gigabit today, which are then shared on top. So each of these customers may get a fraction, 100 max or so. Think nothing that you are interested in. So the answer very clearly, I put it already here, is not a GPON, which is the respective standard, but a WDM PON. That's nothing else but a WDM access system that is as passive as can be. If it has to go, say, for 120 kilometers, there's certainly an inline amplifier side. So it gets active. So what we are talking about in effect will be active PONs. Active, passive, whatever. Our viewpoint is that the respective WDM PON access system needs to be flexible, very flexible. It needs to support various, bandwidth assignments, which means that not only a single wavelength is directed to a single client. Maybe the respective site needs more than one wavelength. Yes, can be done with WDM-PON. Next one is we are not restricted or may not be restricted to physical fiber topologies in a bus tree star way. So if these fibers exist, we could do something like an access ring, which provides protection, which provides bandwidth through multiple wavelengths, etc. And by the way, this node is still passive, or still can be passive. Maybe possibly you need high, or want to get high availability, so either you are after, I'm still talking about transport, and then the respective mechanism would be protection, fast protection in the optical layer, complementing whatever resilience mechanisms in Ethernet layer 3 whatsoever. Now you could go up to dual homing if that is a requirement, and as far as I understood, certain NRANs do use two backbone nodes and try to get access everywhere via both nodes. So that is a typical dual homing scenario. Yes, that can be done with WDM-PON. And if we need well added functionality like longer reach or whatever, we may want to get the option to make the passive remote node active. For example, for an amplifier. So this is what the solution may look like. This is a very generic sketch of a WDM-PON. So obviously this part here is this part protected in this case. Why is only this part here protected? We have other options, as I said, but it would make sense because this part, this so-called feeder part, carries the aggregated traffic, all the wavelength. So whatever happens here to the fiber affects every customer. Whatever happens here affects a single customer. So it might make sense to just protect this part because it can be done very simple, in a very simple way, very easily, very cost effective. The good thing about the WDM-PON, and we are talking, as I said, distances up to 100, 120 kilometers or so, is it then can carry everything. I mean, over 100 kilometers or so, even transport of 100 gigabit per second per channel isn't rocket science. So yes, we can transport a single gig E here, if that is the requirement. We can do 10 gigs. That's commodity today. We can do 40 gig available today. And in a year from now or two, say, we would also be able to carry 100 gigabit Ethernet, OTH, fiber channel, InfiniBand, whatever you want. WDM, by definition, is transparent. Nonetheless, it might make sense to integrate the WDM PON access with some layer 2 functionality, because the two are complementing each other, well, as you know, in quite a good way. It might look like this. This is just one example. So again, overall, this is my WDM PON. Here we have the so-called OLT, which would be based in your backbone POPs. OLT is the optical line termination standard wording for PONs. Here we have the WDM filter. In this case, we have the protection for the feeder part, amplifiers in OLT based. This is allowed in a PON. For reach extension, a passive remote node. Although this is protected, it is fully passive because here it uses a passive optical 3 dB coupler. Then the second WDM filter, the demultiplexer into the region, and the so-called ONUs, the optical networking units, the client in demarcation units. And this could be, for example, a fully blown Ethernet, say carrier Ethernet access unit, providing all the OAM operations, administrations, and management requirements that you may want to get. But this could also be a fully passive device saying the link is alive up to here, and then you could, for example, be an SFP, a little pluggable, plugging directly into one of your switches. So there's quite a range of options. And if that makes sense from the viewpoint of your network structure, we could, for example, also integrate a layer 2, an Ethernet aggregator here, which means this would be one blade going into the WDM PON system, having colored interfaces here, which likely would be pluggables, going into the WDM PON, so lighting up the WDM PON, which would also have colored backbone interfaces, today running 10 gigabit Ethernet and possibly in, I don't know, some future running whatever you want. So this would be quite a powerful combination of transport where the WDM part gives bandwidth, gives reach through the amplifiers, protection in the optical layer, and also you have, or you could get optionally Ethernet functionality for demarcation management. You would get management in-band management channels to access the sites to see that the transport layer is alive and running. You could have aggregation here. Everything would run under one and the same management system using the same DCN. DCN is a data communications network, the logical network that gets you the management access to the network elements. It's necessary in every transport network. Well, and possibly also one at the same control plane, of course. A few last slides on WDM PON versus next generation GPON. Some people obviously, GPON is standardized in ITU, so it's an international standard. And some people obviously found out GPON isn't the answer to everything. It lacks distance capabilities, it lacks bandwidth, and hence there's upcoming something called next generation GPON or XGPON, which from our point of view does not solve the problem, which I will explain. First a slide summarizing the general options for point-to-multipoint access, as I showed on one of the earlier slides. Well, you could go the active point-to-point approach. That's pretty okay. It's scalable, it's manageable, etc. It goes distance. It mainly requires high feeder fiber count here. And if that is not available, this is not an option. So this is the GPON approach, single fiber or fiber pair here, passive power splitter here, and then the distribution fibers. And the problem is the power splitter, which means that this part here is shared, and GPON typically runs a single wavelength for upstream and a single wavelength for downstream. So you have this wavelength once, 2.5 gig, shared amongst all the customers. And WDM PON, well, also gives you the fiber saving here, and then it is demultiplexed by a filter, not a splitter. And on the wavelength level, it is point-to-point, not point-to-multipoint anymore. That's relevant. So in the PON world, these are the two contenders. I'm not referring to active Ethernet point-to-point anymore. This is next. This would be a block diagram of next generation GPON. So this is the original GPON part, maybe complemented by amplifiers for reach extension, and maybe complemented by a WDM overlay. And hey, that may be the answer. I'm now getting a WDM overlay, which gives me the capacity. Yes, but, and I will go into these counter arguments. And this is straightforward WDM PON. So it's simply a filter in the OLT and another one in the remote node, and then you can do anything you want on a wavelength. And by the way, there's of course easier optical amplification here. As you can see, a single EDFA, an EDFA is an optical amplifier, whereas you need certain splitters here and bunch of amplifiers there. So it's more complex in XGPON. the main counter-arguments are reach and security. Reach, that is pretty, or can be shown pretty simply. These are three versions of a WDM PON, unamplified, with amplifiers in the OLT, that is the backbone POP, and with an amplifier in the remote node. And as you can see, it goes some 50 kilometers fully unamplified. Nice. It goes some 70 to 80, depending on fiber quality, with an OLT-based amplifier, so that's approaching the 100, and it goes massively further with a remote amplifier. Whereas in the GPON with WDM overlay, you got stuck in the 20 kilometers arena, unamplified, and even amplifiers in the OLT would only improve this to 30, 40 kilometers. Yes, you could also try to do a remote amplifier which might give the same factor that you can see here, which means it might go up to the 50, 60 kilometer range. And that's it then. This can easily go further. Relevant if you want to reduce your active backbone size. And this is very simple. The other argument, a next-gen GPON still is a splitter PON. So it is a broadcast PON. Everything is broadcasted to everybody, and everybody selects what he wants to get. Which also means that a faulty ONU, a faulty client unit, may physically, technically be able to corrupt the entire PON. Maybe not what you want to get. Plus that, of course, certain customers simply do not accept broadcast for security. In a WDM PON, by definition, you get dedicated bandwidth, physically separated by a filter, and hence you can do anything you want on your dedicated own bandwidth. This is the simple reasons why in broadband access with some security or dedicated bandwidth requirements, a splitter PON is not the answer. This is more or less the summary of what I said. Of course, all of this has some cost effects regarding capacity expenditures, cost of the transport hardware. And what we can see or say today is that even regarding the capex of the systems, a WDM PON nowadays needn't be more expensive than a next-gen GPON. Today, it would not be able to compete with a standard GPON. I mean, a standard GPON transceiver may be as low in capex as some $100 or so. That's impossible with a WDM PON ONU. But I was referring to NGPON. We have the same fiber savings with WDM PON as compared to every other PON system, so that's okay. We can show that the operating expenditures are possibly lower. And that's because a WDM PON avoids specific solutions for certain applications. I mean, it's transparent against every bit rate and against every protocol. It can do possibly any access distance you want to get. Hence, there is no need anymore for any specific solutions that might also be necessary in addition to a GPON. So you can do anything under one and the same system. This is the main OPEX saver. Not that much possible here. And also, in terms of energy consumption, it is pretty easy to show that a WDM PON, although it has massively more interfaces in the OLT, obviously one per wavelength, not one for all. If that's intelligently integrated. It's not a driver in energy consumption anymore. But it's pretty easy to show that for any given requirement for the bandwidth times distance product, and that is what people typically are after. I need that amount of bandwidth over such a distance. This product or that the energy consumption for a given product this product requirement can always be optimized with a WDM PON and not with the other one. So it's even in itself an energy efficient solution, although keep in mind it's part of the optical transport, it's part of the 7%. We are here optimizing something that is a minority contributor to energy already. But even then we can show it's efficient in itself. And far more important is it would help optimize the energy consumption of the total network, mainly by means of its distance capabilities. Yeah, with that I'm through and happy to answer any questions if there are.
Thank you for your presentation. What's the standardization status of the WDM PON and the target to close the standards?
If I understood it right, you are asking for standards in the WDM PON context. Well, today there are none. And but I mean, of course, the WDM PON uses relevant standards from general WDM systems. It of course makes use of it can make use of ITU wavelength. There are some exceptions from that, but so it uses standard or standardized interfaces, standard wavelength, standard amplifiers, etc. The whole system end to end isn't standardized, and I don't see any approaches to that. I mean, the GPON is standardized in ITU, following work done by the FSAN, the Full Service Access Node Consortium. There is a group studying what they call Next Generation Access 2, which might lead to WDM PON, which might lead to recommendations into ITU, but that is years away from now. So possibly we may see WDM PON standards in a couple of years. Another problem might be that there are too many technical approaches to a WDM PON. For example, regarding what is called colorless ONUs, so ONUs that are agnostic to any of the wavelengths. That means you could place any ONU anywhere and it will or would automatically use the correct wavelength. There are technically completely different approaches to that, and I personally doubt that ever will be standardized. However, I don't see to be honest, I don't see a problem in that, because end to end, no WDM transport system is standardized, with the exception of the ITU wavelength and some interface specs like power, sensitivity, etc. And all of this is done in the WDM PON as well. So I don't think the lack of any specific WDM PON standard is a problem. My view.
Our next speaker is Ronald van der Pol. He works at SUFNet, the Dutch National Research and Education Network. He focuses on monitoring and performance in optical networks. So I think your presentation should be here.
Actually, I used to work for SurfNet. Now I work for Sarah, but we are the knock of SurfNet. And this talk is about an analysis we have done on the static light paths in SurfNet 6. These are some first results, so no firm conclusions yet. A couple of words about the SurfNet 6 network. The SurfNet 6 network is the Dutch National Research Network. It's a hybrid network of the traditional IP-routed services and lightpath services. Currently it has around almost 9,000 kilometers of dark fiber. There are 3 cross-border fibers, one to Hamburg, one to Münster, and one to Aachen. And there are almost 200 light paths provisioned, static light paths. This graph shows the amount of light paths in SurfNet 6. The x-axis is the time. It starts at November 2007, and this is today. And this is the amount of circuits. It's not a smooth line, and this is because this is based on circuit identifiers, and we have changed the naming convention a couple of times. But what you can see is that there is a growth in the number of light paths on the network. But from this picture, we cannot tell if it's linear growth or exponential growth. Yeah. SurfNet 6 has 3 types of light paths. Is the unprotected light path. It consists of 1 circuit, and at the customer sides there are the customer gets 1 interface. There's also the protected light path that consists of 2 circuits. The customer still gets 1 interface, and the network takes care of routing through when there is an outage, the network takes care of rerouting the traffic. The last class of light path is the redundant light path. This consists of 2 circuits, and the customer gets 2 interfaces at their site. And the customer has to take care of rerouting traffic when there's an outage or load balancing or whatever they want. And this table shows the current status of the various light paths in SurfNet 6. Most of them are 1 gigabits per second. There are 4 10 gigabits per second light paths, and these are for real customer projects, so not used for the backbone itself. And there is also a relatively large amount of low bandwidth light paths of 150 megabits per second. And the speeds in between, there are not a lot of them. These graphs show the light path duration and provisioning activity. On the right-hand side, this is the provisioning activity. The bottom axis shows the month in so the time. It starts at March 2007, and this is today. The y-axis is the amount of light paths provisioned in that month. Each line box shows 1 week. The green ones are the light paths provisioned, so new light paths. The red ones are decommissioned light paths. This huge peak is an anomaly. This is due to the fact that the software that was used to gather all this information was started at this time. So we have to look at this part of the graph, and then you can see there's a constant activity of light paths, new light paths being set up, and light paths being turned down. At the left-hand side is the duration of a light path. this is the duration. This is 0 days, or well, it's steps of 10 days, I think. Yes. So this is almost a year over here, and this is at the end is 1.5 years. This is again the anomaly that corresponds to this peak, so this is not real there. And this is the amount of light paths of a certain duration. And this, we have done this mainly to see if there were a lot of short-lived light paths. You could expect that when there's many short-lived projects, that there's a lot of, there would be a peak over here that would show light paths that were only active for a couple of weeks, for example, the duration of a project. But we don't see that. Most of the light paths in SurfNet 6 are long-term light paths. A couple of words about the tools we have written for these analysis and also for managing the light paths in SurfNet 6. We have a light path planning tool. This is used for finding optimal paths in the network for new light paths. It's in-house built, open source. It's written in Java, based on Java server pages and servlets and Apache Tomcat. For unprotected light paths, it uses the Dijkstra algorithm. For protected light paths, it uses the Zuurballe shortest cycle algorithm. And for shared risk link group constraint-based protected light paths, we use an adapted Dijkstra algorithm. I will come back to that later. The tool also has a configuration file that uses regular expressions to set metrics to different parts of the network. For example, we can set all the interfaces in one POP to a certain metric, or the metrics on certain links to, or the cost of certain links to a specific metric. And we have also a cost-based, a metric based on utilization. The planning tool consists of 3 main parts. One of them is the TL1 toolkit. It's written by Sarah. And this is a script that retrieves all the information from the network. So which light paths are in the current network, which resources are used, which interfaces are used, etc. And it also retrieves the topology of the network. It retrieves the topology from the network automatically. This topology is put in an NDL description, network description language description. This is the framework developed by the University of Amsterdam. And this is used to describe the topology of SurfNet 6. Okay, finally we have the configuration data, which I just mentioned. And this is stored in a MySQL database. And the analysis we have done is based on this MySQL database. These are again the major parts of the software. The SurfNet 6 network, the TL1 toolkit. TL1 toolkit retrieves information from the SurfNet 6 network, stores the configuration information of light paths in a MySQL database. It stores topology information in an NDL file, and the configuration database and the topology information are used by the light path planning tool to find paths for light paths in the network, and that's presented to the user via a web interface. The algorithm used by the tool is we read the NDL topology file, and we build a mathematical graph. Then we read the current configuration data from the MySQL database, and we remove all the links that don't have enough capacity for the light path that we are planning. And then we run a pathfinding algorithm, so either Dijkstra or Suurballen. We find a path and reserve that in the database. This is the user interface of the planning tool. Here we can choose the endpoints. This is used to include or exclude certain interfaces in the network. So we can play around with these to have a light path go through a certain site or avoid a certain site. We can choose a protected light path or an unprotected light path. And then this is the information that the tool provides. The primary path and the backup path, information about the metrics, information about the interfaces and the time slots used. And this can be used to provision the light path in the network. Recently we have started work on finding paths considering shared risking groups. A shared risking group is the case where fibers are going through the same duct or wavelengths going through the same fiber. You have to make sure that your primary path and backup path don't go through the same ducts, through the same shared risk link group. And there is not an algorithm for finding a path like that. It's an NP-complete problem. So we have used some heuristics. Fortunately, the SurfNet 6 network doesn't have a very difficult topology. We made use of that. Yeah, and because there's a limited number of possible paths, we can run an algorithm that gives an answer in reasonable time, usually less than a second. This is an overview of the WDM layer of SurfNet 6. It consists of a couple of rings. This is one site in Amsterdam, this is another site in Amsterdam, and all the rings start at one site in Amsterdam, go through the country, and come back to the other site in Amsterdam. And this makes the topology relatively simple. It's just a couple of rings. With this planning tool, we have done some analysis of the current provisioned light paths in SurfNet 6 to see if they are still, or if they are optimally routed. This says 300 light paths. It's actually around 200 light paths and around 300 circuits. And this is because, for example, the redundant light paths consist of 2 circuits. And we have the question, are these 200 light paths, are these optimally routed? Because when we started the SurfNet 6 network, the first light paths were manually found in the network, so it was not a computer algorithm that chose the shortest path, but it was a human being who tried to figure out the shortest path. So the first light paths were not optimally routed. And also the network evolved, the topology changed. The first version of the planning tool didn't use the Suurballen algorithm, but used 2 times Dijkstra. And it is known that that doesn't always provide give the optimal path. So these are some reasons why we believed that not all the light paths were optimally routed. And what we did was we did a replanning of the light paths in 2 ways. One was take one light path out of the network, free up the resources of that light path, and replan that light path in that network. And the second one was remove all the light paths and replan all the light paths in an empty network. And the result is like this. We found that only 47 of the 200 light paths were not, or actually this is circuits again, so 74 of the 250 or so circuits were not optimally routed, but the other 150 were optimally routed. We have to take a closer look at these 47. What we also found is that there was no difference between rerouting on an empty network or just taking out one light path and replanning that one. And this is due to the fact that the current SurfNet 6 network doesn't have any resource limitations at the moment. So we can, in principle, replan all the light paths that are currently in the network in an optimal way. And I've given a couple of examples at the bottom. These are the number of interfaces that are used for these 4 light paths in the currently on the network. So this light path is using 6 interfaces. And the optimal light path that we can use is 4 interfaces. So we can save 2 interfaces. For this system, we can also save 2 interfaces. All of them we can save 2 interfaces. So if we replan these 4 light paths, we save already 4 interfaces. And we have to look carefully at all those 47, look manually at those and replan all those that can be more optimally routed. And then we can free up a lot of interfaces on the network. So this was a useful exercise. That is my talk.
Thank you again for your presentation. My question is, in your pathfinding algorithm, do you consider the analog impairments of the fiber? I mean, chromatic dispersion, PMD, attenuation, nonlinear effects?
This is all done on the SDH layer. So we don't need to consider dispersion and things like that. The topology that is used for planning these light paths is just a simple graph, point-to-point links, and we don't if there are enough time slots, then we can use that path.
Okay. Hi. There was a question yesterday, but I couldn't hear the answer. What's the signaling protocol you are using for provisioning?
What we currently do is we use this planning tool to figure out which route we can use for the light path. And then it's a sort of manual process using the network management tool of the vendor to provision the light path. So it's not done by GMPLS or something like that. It's a network management system.
Okay. Then a more general question about GMPLS, or anybody else can also answer. What's the current situation with that, and also with this LMP link management protocol, because it already contains RSVP, which can do this optimal routing, but there is a lot of solutions which are doing now it in their own ways.
Yeah. SurfNet 6 supports at the moment 2 types of light paths. One of them is the static light path, and that is done with the network management system for the provisioning. And the other one, it's the Notel Direct software, and that is used for dynamic light paths. That's basically that uses a web interface And it's also a system. It's not using GMPLS or something like that, but it's used for dynamic light paths.